Honors Chemistry, and welcome to 13.6 Molarity. So in the previous section, we talked about mass percent and how to use mass percent, which again is the life version of concentration. Molarity is the science version of concentration, right? And molarity is moles of solute per 1 liter of solution, right? And so note that it's different than the concept of mass percent, right? And every time we see capital M, we should know, that means molarity. And so every time I see this concept, right, so if I see a 2.0 molar solution of NaCl, I should think to myself, capital M, molarity. Molarity is a relationship / conversion factor. I'm going to rewrite it as its two representative pieces so that I know what to do with it. So we will take that and say that there are 2 moles of NaCl equal to every 1 liter of solution, or NaCl aqueous, right? Or solution, right? That's what that means, right? That is the amount of dissolved NaCl per that volume of solution, yes? Now, your book goes on to say that you need to be mindful that when we make our solutions, right, volumes change when we add a solid solute, right? So for example, your book talks about how if we add 1 mole of NaCl to 1 liter of water, it's not necessarily true that the volume of solution is going to be 1 liter, right? Because at NaCl, right, that takes up space. So does the water, right? Sometimes it's true that the attractive forces between our two, my solute and my solvent, are such that they mix so well that the volume remains unchanged, right? But sometimes they don't and the volume expands. Sometimes they mix so very well that the volume actually gets smaller, right? And so these are all options. So it's not okay to just say, I added 1 liter of water and added my salt and I made 1 liter of solution, right? Does that make sense? Going back to what's in your book. So then, if we wanted to prepare a 1 molar solution of NaCl, and it is expected that you could describe how to do it, right? We would measure out 1 mole of NaCl, right? And we could measure out how much 1 mole is by using its molar mass, right? So then that's 58.44 grams of NaCl, and we would add that to our vessel, right? In this case, they are using a volumetric flask, where volumetric flasks are very specialized pieces of laboratory equipment that are designed to measure literally 1 volume, right? So if you look there, it has a 1 graduation, just 1, right? But it's typically known to 2 decimal places, right? So we are getting, so for example, this is 1 molar, right? 1 liter, right? Which means this is 1.00 liters exactly, right? We get 2 decimal places on there, so we get 3 significant figures, which gives us more precision than we could get if we were using a beaker, right? If we think back to when we talked about in chapter 2, right, beakers are not used to get accurate measures of volume because they are so poorly graduated, right? We would be lucky to get 1 significant figure off of a beaker, right? So if our goal was only 1 significant figure, we could use a beaker to make our solution, right? But anything more than 1 sig fig and a beaker would be insufficient, okay? But note that volumetric flasks are only necessary if we're trying to get 3 or more significant figures, yes? Okay, so anyway, we would add our solid, then we would add water, right? And after we add the water, we would swirl until our stuff starts to dissolve. And once it's dissolved, then we would top it off to that mark, yes? So those are the steps that we would do. Measure out your solid and add it, add some water, swirl to dissolve, then top it off to the graduation, right? All right, so then let's do a few practice problems together. So it says, calculate the molarity of a solution, right? So if I want to find the molarity, that means I need to get moles per liter, right? Are made by putting this many grams of my solute, right, into a beaker and diluting it to this. So this is the volume of my solution, right? Because it says that's what my final volume I reach, right? So then if I want to get moles per liter, I'm going to go ahead and take my 55.8 grams of sodium nitrate. And I got to get that into moles using, that's right, molar mass, so 85 grams of NaNO3 for every 1 mole of NaNO3. And if we think about what's happened, right, we've canceled out grams. And then moving along to the next thing, right, now I'm at moles, and now I just need to do what? Right, divide by liters. So I'm going to say 1 over 2.50 liters of solution, and this is going to get me moles per liter, right? Alternatively, if you don't like how that looks, right, you could stop here and just take that number, right, and then divide that by 2.5 liters, right, to get your molarity, right? And that would be fine as well. Yes, does that make sense, right? If you don't like how that looks there. Okay, next up, it says how much of this molar KCl is needed to contain that much KCl, right? So I want to talk about my solute. This is my given, right? Grams of solute, and I have a molarity. Here is where, again, if you write this out to yourself, you're more likely to use it correctly. So that means I have 0.225 moles of KCl are equal to every 1 liter of solution, right? So now we can work with that, right? And by solution, I do mean KCl, aqueous solution, right? So let's start with our grams of KCl because that's our given, 55.8 grams of KCl. And then I will convert that into moles because that's what I'm going to need here, right? So that would be, this is the molar mass of KCl for every 1 mole of KCl. Now I can employ my molarity, right, which says that there are this many moles of KCl for every 1 liter of my solution, right? Now, when I do this, I'm going to get the volume of solution, right? So volume of solution, meaning something that I can measure out in a graduated cylinder, right? How much of the solution I need if I'm trying to get 55.8 grams of KCl. Yes, does that make sense? All right, next up, determine the molar concentrations of these things in 0.75 molar CaCl2, right? So here, let's write this out again. So 0.75 moles of CaCl2 are equal to 1 liter of CaCl2 aqueous, right? So now what we'll do is if we want to talk about molar concentrations of each of these, right, what we're going to do is we're going to just have to write some relationships, right? So 0.075 CaCl2, moles of CaCl2 for every 1 liter of CaCl2 aqueous, right? Now, I know that 1 mole of CaCl2 contains how many moles of calcium? Right, contains 1 mole of calcium, which means that I have 0.75 molarity, right, calcium ions in my solution, right? Or I could say 0.75 moles of Ca2 plus per every 1 liter. And that would be okay also, right? Whichever way to express that you would like. And for the other half of that problem, right, I would simply say 0.75 moles of CaCl2 for every 1 liter of CaCl2 aqueous, right? And for every 1 mole of CaCl2, there are 2 moles of chloride ions. Yes, going back to what calcium chloride is made of. It's made of 1 calcium cation, 2 chloride anions, and that is going to give us our concentration of chloride ions. Yes, right? Which means that the concentration of chloride ions is double that of calcium ions. Yes? And in total, for every 1 mole of calcium chloride, our solution will be filled with 3 moles worth of ions. Yes? All right. Thank you for listening. Be good and stay tuned in the next one where we talk about the concept of dilutions. All right. Be good.